Hi, my name is Ravi. I'm a fifth-year PhD student at Stanford. I work with Professors Hito and Benz and Vasilis Syrgkanis on causal inference. Today, I'm going to tell you about dynamic local average treatment effects. So one setting you may think about using this is in marketing. So say you're trying to maximize holiday season gross profit. One thing you may want to do is target incentives so that people transact same day. And you may do this by targeting incentives to people who express purchase intent in the past. So in this example, non-members are our target population. Purchase intent here will mean you visited checkout but didn't quite transact. And by checkout, I mean you confirm the order and you're initiating the transaction. And we're interested in the people who did not buy, maybe because the people who bought are less likely to transact again so quickly. So if you express purchase intent yesterday and go to checkout today, you get an incentive, and here the incentive will be free membership benefits for a week. So that's the example. I have to give some notation so I can state some theorems. S represents states. Here, that's purchase intent. In this example, the account didn't express purchase intent, so we don't give an offer on time step one. And since they don't get an offer, they can't redeem. And but they can still visit the checkout on day one. So if they do that and don't buy, we can give an offer the next day, and maybe that leads them to redeem. And then there's some outcomes. Here it's holiday season profit. So one question you might ask is, after the holiday season is over, can we improve efforts the next year? The current year, we targeted incentives to get same day transactions, but after the holiday season's over, you have longer term outcomes. So it'd be really nice if you could look at the data, find the people who redeemed, and if we increase their profitability, maybe they use extra services that were free, advertise those or offer those directly. One thing you don't want to do is compare people who redeem to those who don't. This offer is being made at the checkout page, so a lot of people are going to redeem anyway, or transact anyway. So what that'll mean is the difference is going to be positive. And you can actually have an effect that's negative and still have this difference be positive. And the effect might be negative, for instance, if people are just using the free services. So what we want is the effect of redeeming. And it'd be nice if this effect of redeeming is relatively larger than the effect of the offers on average, because it means it is a subpopulation for which something is working. So just to review notation, this is dynamic because the offers depend on previous states. There's non-compliance because not everyone is going to redeem the offer. And then there's unobserved confounding between states, outcomes, and treatments. And this is the identification challenge. So the way we're going to address it is by extending the identifying assumptions in Vincent Angus, 1994. This is a seminal paper of local average treatment effects. So we'll extend the assumptions so that conditional on the history of random variables, the assumptions hold in the next time step. And then we're going to get rid of monotonicity and replace it with one-sided non-compliance. Informally, this says that if you're given an offer, you may or may not redeem, but you definitely can't redeem if you're not offered. So if you make those two changes, you can identify the effects of treating one time period and setting the rest of control. And the formal estimate is this right here. So the average impact at outcome Y of treatment sequence D relative to never treating for the subpopulation who would redeem with offers Z. And then this effect of the treatment D on outcome Y is equal to a ratio of effects of offers. The numerator is this effect of offers on the outcome, and the denominator is the effect of offers on the treatment. And this is identified because all those counterfactual averages equal estimable functions of the observational data distribution. So you can also do this for another estimate we call the local intent to treat effect. This is the effect for the people who redeem in any time period, as long as it's at least one time period. And this is also an effect of a treatment on an outcome for some subpopulation, and it's equal to a ratio of effective offers, one on the outcome and the other on treatment. This is also identified because all the counterfactual averages are equal to functions of the observed data distribution. We can also identify effects of treating multiple time periods. The way you do that is you take the assumptions of the previous theorem, add one more. Find me at the poster because it's kind of complicated to talk about, but it's satisfied if you have staggered adoption, where once you're treated, you remain treated, as in the case of membership. You get this identification result, and if you want to satisfy it some other way, it turns out that you'll have to apply a correction term. So you have a ratio of effects of offers minus this correction term, but it's all identified. And we have more identification results in the paper. I still have to upload another version. There's more results, but we already have estimation inference results for multiple time period simulations, heterogeneous effects. And yeah, I just want to say there's other settings with non-compliance and dynamic offers. Thanks.